Hopefully you've done or watched the preview video on simple harmonic motion and how it compares to circular motion. We're going to continue our analysis of simple harmonic motion. I'll be referring to that video every now and then. So the period of simple harmonic motion, primarily right now we're talking about a mass on a spring oscillating up and down, but it can compare to other things that are in simple harmonic motion also, like a pendulum. So the period of a simple harmonic oscillator depends on the spring constant and the mass of the oscillating object on a spring, not the amplitude. A mass oscillating in simple harmonic motion is similar to an object rotating in a circle, as we saw in that video. We're going to expand on that information. So this is an object moving in a circular path. And we're going to look at the horizontal displacement of that object as it's moving through the circle. Of course, if this object started right here, that horizontal displacement would be the entire radius of the circle, which we would call the amplitude, which is the maximum displacement from rest position. As it goes up this way, its horizontal displacement gets less and less and less. And when it's right here, this horizontal displacement is zero. It is in equilibrium. And it comes down here, has a maximum displacement again, and it just keeps oscillating around. If we look at it on a side view like this down here, we would rotate this table 90 degrees. We're looking at it straight on. This mass would look like it's oscillating back and forth like this, just like it did in the video with that yellow marker cap that was spinning on that turntable. So let's take a look. Some things that we know. We know that the maximum velocity of this object moving in simple harmonic motion is 2 pi a times the frequency. We know frequency is the inverse of the period. So we can write this 2 pi a over the period, because the period is just the inverse of the frequency. Now let's take a look at this equation for a little bit. 2 pi a, again, the amplitude, is the maximum displacement, which is the radius of this circle. So this is actually 2 pi r times the radius, which is divided by the period, which is one time it takes to go around that radius, so that's the time. So this is circumference over time, which is distance over time. That's the velocity, the maximum velocity of that. So that we've used this equation before to determine the speed of an object moving in a circular path, distance over time, circumference over time. That's the same as this equation right here, but this is the maximum velocity for that situation, all right? So now, let's keep going with this a little bit. I'm going to rearrange this equation to solve for the period. So the period is going to be 2 pi a over the maximum velocity. And we have another equation for maximum velocity for object moving in simple harmonic motion. We've derived that previously. The maximum velocity is equal to the amplitude times the square root of k over m, the spring constant over m. I'm going to move the amplitude to the other side of the equation, so this will be the maximum velocity over the amplitude is equal to the square root of k over m. Well, look what we have in this equation. We have a over maximum velocity. This is maximum velocity over a, which is the inverse of this. So what I can do, so this maximum velocity over a is equal to the square root of k over m. Since this is the inverse of this, I have to invert this. A over maximum velocity is equal to the square root of m over k. I have to invert that. So now I'm just substitute it into this equation here, a over maximum velocity. This period is going to be equal to 2 pi times the square root of m over k. And this is the period of a spring. And this is the equation that's on your equation sheet for the period of a mass oscillating on a spring. Take your equation sheet here and take a look at that. This is the period of a spring, 2 pi times the square root of m over k. That's where that equation came from. So that's the derivation of this equation. We'll take a look at a couple more things here on this. If we take a look at this angle, and this is the adjacent side, and this is the hypotenuse, so that's cosine of that angle is equal to the adjacent over hypotenuse, which is x over a. I'm going to solve this equation for x. That's going to be a times the cosine of theta is equal to x. I'm going to rearrange it so x is on the left side. This is x is equal to a times the cosine of theta. This is the cosine equation that relates the displacement of an object in simple harmonic motion to its amplitude. And so we're going to come back to this equation. We've used this as, in one of the problems that we had for our graded homework, but we're going to expand on that as we go through this also. One more thing. We know, we take this equation right here. Remember, the period is the inverse of the frequency, the frequency is the inverse of the period. So if I write frequency, it's going to be the inverse of this equation. It's going to be 1 over 2 pi times the square root of m over k. I'm going to rearrange this equation. I'm going to put 2 pi on the left side, so it'll be 2 pi f is equal to the square root of m over k. I'm going to get rid of the square root. This is going to be 2 pi f all squared is equal to, I'm sorry, this should be, made a mistake, this should be, I have to inverse this should be k over m. This is k over m, sorry about that, k over m. So this is equal to 2 pi f squared times k over m. Right? Now, we know that an object that is moving in simple harmonic motion, it is changing velocity, so that means it's accelerating, so there must be some net force on it acting at various places. And Newton's second law says net force equal to mass times acceleration. I'm going to solve this equation for acceleration. Let's rearrange it a little bit. Acceleration then is going to be equal to the net force over the mass. Now, that force for a spring oscillating back and forth follows Hooke's law, F equals kx. And if this x is at its greatest displacement, that means this net force, this maximum force, is at its maximum displacement, which would be Ka. So this net force is Ka. So then I'm going to substitute in Ka into this equation. So the maximum acceleration of this object occurs at its maximum displacement, or its amplitude, and that's going to be equal to Ka over m. Well, look what we have here. This is K over m. We have K over m here. So I'm going to put in here the maximum velocity of something moving in simple harmonic motion is equal to 2 pi frequency all squared times the amplitude. It's a good equation to know. Okay, this is not on your equation sheet, but it's a derived equation. Just to note, I'll be giving some other information about the AP exam at the end of the year. And what I've been reading so far is that you can actually use your notes on the AP exam. So the better notes you have, the better organized your notes are, the better you're going to be. Okay, so that's a good equation to know. All right, let's continue on. See if we can solve a problem using this information. This is example problem 1. This information, a spider of mass 0.30 grams, so this mass is 0.30 grams. Of course, we're using force and period and so on, and spring constant is in newtons per meter. That's going to have to be in kilograms. Like I said, you don't have to show one-step conversion, so it's actually going to be 3.0 times 10 to the minus 4 kilograms. Weighs in its web of negligible mass. A slight movement causes the web to vibrate with a frequency of 15 hertz. So the frequency is going to be 15 hertz. Determine the value of the spring constant for the web. This web acts like a spring. It oscillates back and forth, similar to the characteristics of a spring. So then we want to determine the spring constant. Well, we know that the period of the spring is 2 pi times the square root of mass over k. We know the mass. We are given the frequency. But if we know frequency, we can always get the period, because the period is equal to 1 over the frequency, which is 1 over 15 hertz. which is going to be 6.7 times 10 to the minus 2 seconds. We put this information in this equation, it's going to be 6.7 times 10 to the minus 2 seconds equals 2 pi times the square root of the mass, which is 3.0 times 10 to the minus 4 kilograms, divided by K. We solve this equation for K, and we get 2.64 newtons per meter. Let's look at B. At what frequency would you expect the web to vibrate if an insect of mass 0.1 grams were trapped in addition to the spider? So now the mass of the insect is 0.10 grams, which is equal to 1.0 times 10 to the minus 4 kilograms. But the insect isn't, the mass of the insect isn't the only thing that's oscillating. You also have to include the mass of the spider. So the total mass is going to be the mass of the insect, 1.0 times 10 to the minus 4 kilograms, plus the mass of the spider, which is 3.0 times 10 to the minus 4 kilograms. So that total mass can be 4.0 times 10 to the minus 4 kilograms. We want to know the frequency that's oscillating. So again, we can use the period of a spring is equal to 2 pi times the square root of m over k. We can solve for this period because the spring constant is the same for both situations. The mass doesn't change the spring constant. So we can solve for this period, which is going to be equal to 2 pi times the square root of the total mass, 4.0 times 10 to the minus 4 kilograms, divided by the spring constant, 2.64 newtons per meter. We get that period of the spring to be 0.077 seconds. Of course, we want the frequency, not the period, which is 1 over the period. It's 1 over 0.077 seconds. We get that frequency to be 12.99 hertz. I'm going to round that to 2 significant digits, 13 hertz. That. All right, now let's go back to the position as a function of time, which is basically this equation right here. I want to expand on that a little bit. Like I said, we already had to use that equation for one of the graded homework problems, but we're going to expand on that and see if we can understand it even more. So we have this that we start with. X is equal to a cosine of theta. Now, theta, angular distance, is also equal to the angular velocity times time. So for this equation, x is equal to a times the cosine of angular velocity times time. Of course, angular velocity, we've already seen, is 2 pi times the frequency. So for angular velocity, x is equal to a times cosine of 2 pi frequency times the time. So at any period of time, this isn't just, at any time period, we can determine where that object is located as it's moving in simple harmonic motion. Remember, object moving in a circular path creates a sine wave or a cosine wave. We have cosine written here, but the only difference between sine and cosine is that they're 90 degrees difference between when we start analyzing the motion. So this is what we have. X is equal to a times the cosine of angular velocity times time. Of course, angular velocity is 2 pi f, so that can also be equal to a times the cosine of 2 pi f times the time. But remember, depending on where we start the analysis of the motion, whether it's at the top of its path or the middle of its path, we'll determine whether it's sine or cosine. So this can also be a sine angular velocity times time, or a sine 2 pi f times time. You can use either of those equations, just depends on where you start the analysis, but they both work exactly the same. All right. Let's see if we can do some example problems using this equation in our understanding of simple harmonic motion. All right, let's take a look at this equation. You should be able to, from any sine or cosine equation that describes the displacement of an object in simple harmonic motion, you should be able to understand the variables or the numbers in this equation to answer different types of questions. So let's take a look. Determine the oscillating object's amplitude. Again, if we come up here, let's make sure we understand what this is. This number in front of the cosine is the amplitude. And remember, this right here is the angular velocity, which is also 2 pi times the frequency. We keep those in mind as we go through. So amplitude is simple. The amplitude is simply 0.30 meters. We can take that right from the equation. The frequency, remember, angular velocity is 2 pi f. The angular velocity is 8.0. This has to be in radians per second. So this is 8.0 radians per second equals 2 pi times the frequency. If we calculate that frequency, we end up getting 1.27 hertz. The period is equal to 1 over the frequency. So if we know the frequency, we know the period. If we know the period, we know the frequency. Just 1 over 1.27 hertz. We get that period to be 0.787 seconds. The maximum speed. Remember, an equation for maximum velocity for an object in simple harmonic motion is 2 pi AF. We now know the amplitude and the frequency for this system. The maximum velocity is 2 pi. The amplitude is 0.30 meters. And the frequency is 1.27 hertz. We get that maximum velocity to be 2.39 meters per second. Remember, the maximum velocity occurs at its equilibrium position. At its maximum displacement, the velocity is actually 0. Then it has any velocity between its 0 and its maximum velocity. The maximum acceleration, we have an equation that we derive for that. Maximum acceleration is 2 pi frequency all squared times the amplitude. We know both the frequency and the amplitude, just like we had up here. So this maximum velocity is going to be 2 pi. Whoops, the frequency is, let's put the 2 pi. The frequency is 1.27 hertz. You want to square all of that. Make sure you understand all this is squared. And the amplitude is 0.30 meters. That maximum acceleration, again, the maximum acceleration occurs at its maximum displacement from equilibrium position. And that should be 19.1 meters per second squared for that maximum acceleration. All right, let's see if you understand. I'm going to skip this problem number 3. I think we can do that. Let's go to page 12 on here. And what I want you to do is pause the video and notice this is a similar equation that we just had, similar types of things that you need to solve for. Just looking at this equation, see if you can solve for those values there. You can pause the video, do this problem, and then start the video again, and you can check your answers. Go ahead and pause the video. All right, you have the solution done. Let's take a look and see. This is actually sine. So the answer should be 0.5 meters, 1.91 hertz. This is 0.523 seconds. This is 6 meters per second for maximum velocity. And the maximum acceleration, 71.9 meters per second squared. Of course, you can pause the video anytime you want to check your answers with mine. See if you got anything wrong. Make sure you have the correct solutions there. Right? Almost done. We have one more set of notes to do. And I have the derivations on this page. I just want to talk through them. This is the period of a pendulum. Right? And remember, a simple pendulum as we saw in that introductory video, consists of a small object, and the simple pendulum oscillates back and forth in simple harmonic motion, just like a mass on a spring. Now, on your equation sheet, let me see if I can find that equation sheet again. On your equation sheet, This is the period of the pendulum. This is the period of a spring. Notice there's a mass that affects the period of the spring, but there's no mass that affects the period of a pendulum. Let's see why that is and why we get this equation. Again, you can pause the video at any time to review this information or write it down. I'm going to go through this kind of quickly. One of the main things we need to understand is that this angle is small. If we look over here, if we determine that angle in radians and take the sine of that angle, that as long as we have a small enough angle, the angle in radians and the sine of that angle are almost exactly the same until we get to about 15 degrees. After 15 degrees, we start getting a little more significant difference between the angle in radians and the sine of that angle, sine of theta. So that's an important thing to kind of remember as we go through this. We're going to use that as a simplification to solve this problem. Now remember, this angle is very small. If this angle is small, that means this distance, linear distance here, and this arc length are pretty much the same distance. So just keep that in mind as we go through this. All right, so I'm going to take a look at this angle right here. I'm going to take the sine of this angle, which is the opposite side, which is this x distance right here, and the hypotenuse, which is the length of, remember, this distance and this distance are virtually the same thing. So this is the x displacement here. And so this is x. This is the length of the pendulum. Sine is opposite, which is the x displacement over the length. So we get sine of theta equals x over L. And then if we solve this equation for x, L times sine of theta is equal to x. That's why I have L sine theta there. It's the same thing as x, this distance. Remember, this distance, as long as the angle is small, that distance and this arc are about the same thing. So this sine of theta, as long as theta is small, is the same thing as theta in radians. So this sine of theta is equal to theta in radians, so we can write this as L theta equals x. We rearrange the equation for theta, we get theta equals x over L. Now let's take a look at this. We have, let's take a look at the forces. This is the force of gravity straight down when this pendulum is up at its maximum displacement. This vector can be broken up into its y component. This is kind of like an incline. This can be its y component. This is its x component. They have the x component drawn up here. It's moved it down here to show that this y component, this x component add up to be that resultant vector. So I'm going to take the sine of theta is equal to the opposite side, fx, over the hypotenuse, which is mg. I'm going to rearrange this equation for fx. So mg times sine of theta is equal to fx. But remember, as long as that theta is small, theta in radians is the same as sine of theta. So I'm going to write this as mg theta is equal to fx. I'm going to just switch this, fx equals mg theta. Remember, theta is x over L. So I'm going to put in here mg times x over L. Now, mass and acceleration of gravity and length are all constant. The only thing that changes this x, it goes back and forth, actually goes all the way back and forth this way. The x displacement is changing, but the length doesn't change, the mass doesn't change, the acceleration of gravity doesn't change. So I'm going to move this L over here. It's the same equation with mg over L times x. This is the constant for that simple harmonic motion. Notice this is Hooke's law, which is F equals kx. This is the same thing, F equals a constant times x. This constant for a pendulum is mg over L. So I'm substitute that into this equation times x. Now, this mg over L is the constant. This is the equation for the period of an object in simple harmonic motion, or a spring, is 2 pi times the square root of m over k. Well, the k for a pendulum is mg over L, so I'm substituting mg over L in for k here. Masses cancel out. Again, this is 1 over g over L, which ends up being L over g. So this is the equation for the period of the pendulum. Notice that is the equation that is on the equation sheet, period of a pendulum, 2 pi times the square root of L over g. As we saw in one of the very first videos that I did with different mass pendulums, the mass of the pendulum had no bearing on the period. It was only the length of the pendulum, and of course, where the pendulum is located on Earth or the moon or some other location, which is on the surface of the Earth. It's the acceleration due to gravity. So this is the equation for the period of the pendulum. Of course, we want the frequency. You simply have to invert that, or just figure the period and take the inverse of that. All right. So we're done with chapter 11. That is the last chapter that will be included in the AP exam. Check the LMS for homework, and I will be hopefully giving you more information about the AP exam either tomorrow or the next couple of days as we go through this.